Hi, my name is Will Fancher, and today I'm going to talk about what NixOS calls stage 1 and how we're using systemd to improve it. Now, a lot of you might know me better as Elvis Jericho, which is how I go on GitHub and every other online platform. It's a little bit of a silly name. It's not like initials or anything like that. Bear with me, I promise this is relevant. So I have this name because when I was in middle school, I was trying to sign up for some online gaming service, and I tried this name and that name, and after a million tries, eventually the gaming service just gave me this suggestion and told me to use it, and I was like, okay, it's spelled a little weird, but whatever. So for a long time, I tried to keep it anonymous, where it was the name that only my friends knew, and only my friends knew that Elvis Jericho was Will. But eventually I started using it to contribute to open source, and that quickly dissolved. So nowadays, this name is effectively synonymous with me. And it highlights something that I've learned, which is that these very small decisions that we make can end up having very influential effects on our lives. And so that's what I want to talk about with systemd stage 1 and what we've done to bring that into NixOS. So first of all, what is stage 1? It is a terminology that is pretty unique to NixOS. Most distributions and other products will call it something like initrd or initramfs, but we tend to prefer calling it stage 1 because it refers better to the time period during boot that we want to talk about. Initrd or initramfs might better describe the particular file format that you're using to represent this concept. But with that out of the way, stage 1 is the first user space code that the kernel calls once the kernel is started up. So when your bootloader gets going, it loads up your kernel, and it loads up a initrd archive, and then the kernel unpacks that into a memory file system and runs its init process as PID1. And its job is to find and prepare your operating system. We do this in a separate stage rather than in the bootloader because by harnessing the power of Linux, we can do drastically more complicated things with it. And that can include things like disk encryption or network systems or many other things. But the main job is to mount the root file system and other what I'll call core file systems. These refer to things like the Nix store or the etc directory that will populate with etc files and things like that are necessary to start the operating system. Once all of this is done, the operating system can start, and that means that we will find the init process for stage 2, and we'll switch root to the new root file system and exec that as PID1. And now the actual operating system gets to start, and we leave the realm of stage 1. Also, you do have to do NixOS activation, which, when that happens, depends on if you're using the old initrd versus the new initrd. We can talk about that later. So what we have right now is called scripted stage 1. And it is effectively just this shell script and these options. This shell script is just this, I think it's a couple of hundred lines long or something like that. Oops, I think I just turned it off somehow. Can I be heard? Oops. I touched something with the keyboard. Try now. Are we back? Hey, okay, cool. So, yeah. To future speakers, don't touch that particular switch. So this shell script is it is the sequence of steps that need to be taken by just about any installation of NixOS. And it is influenced by these other options. The first one, the file systems option, gets passed into the stage 1 script, and the stage 1 script will iterate over all of your file systems, particularly just the core ones, Nix store, the root file system, and all of those. And it'll mount those, and this script has knowledge of how to do that best. So it knows which ones it needs to run a file system check on, or which ones that needs to be skipped. It knows which ones it needs to modify some of the parameters for. But the main job is to mount those file systems. But NixOS also has a lot of abstractions that get added into the initRD, things like LUKS encryption, networking, Clevis, and a variety of others. And these are always implemented in terms of these other 4 options. Things like pre-device commands, post-device commands, and all that. These are command or like little shell script fragments where you can assign to one of these options just a fragment of shell scripting, and that will get interpolated directly into a certain spot in this script file. And so the pre-device commands option, for instance, gets substituted into the script just before we start udev. The post-mount commands gets interpolated right after we've finished all the mounting, right? So these things all happen at specific points in time. So, but what is the problem? Well, it's one of those little things. You see, I found this one option in particular that bothered me quite a bit when I first saw it. It's this boot initRD LUKS devices pre-LVM option. And this one's really weird because what's happening is when you set up a NixOS system on an encrypted LUKS device, you have to tell NixOS, well, does that LUKS device get unlocked before we find LVM devices or after we find LVM devices? And that's just a little weird because it's a dependency that is, there's only one way to do it, right? One way to configure it. In theory, this could be arbitrarily complicated, right? You could have a LUKS device on an LVM device on a LUKS device on an LVM device and so on, as much as you wanted, and insert whatever complicated thing that you wanted in between. And this will not allow you to represent that, so you would have to do something custom. The other thing is that this whole thing is serial and imperative. It's just one big shell script that does one thing at a time, and it's all written in this very shell scripty kind of way. And probably the worst part is that it's all custom. There's a lot of custom code. So we have just hundreds of lines of shell scripting that just implements a lot of logic that is all done serially, and it's all a little codependent, and it's really awkward to maintain, and it's frustrating to write. So what about systemd? Well, so first of all, systemd is PID1 on an NixOS system. Its main job is to bring up your applications and your services. And it'll do so using what's called, or well, rather I should say, it manages the processes, the mount points, and the devices that can constitute a functioning system, which is to say, like, when you have NixOS running, it is keeping track of what processes are running, where your file systems are, what devices they depend on, and like how all of these things interact with each other. And it does so with a concept that is called units, which is a declarative concept. There's a lot of different types of units, but the 3 we're going to focus on are services, devices, and mounts. And a unit is just, it's a logical construct that exists in this graph, this dependency graph that says this unit depends on this unit, and this unit depends on that unit, and it allows you to specify things like arbitrary ordering, where you can say this one needs to be after this one, but I don't care how it relates to this other one over here. So this allows you to make very complicated logical graphs of how you want the system to start up. And what's important is that these things are declarative and they're parallel. So these things can start up whenever they're needed, as soon as they're needed. And you don't have to like write code that just says do this, then that, then this, then that. You get to put a unit exactly in the graph where it belongs, and systemd takes care of the execution. So if we put this in systemd, or in stage 1, sorry, it comes with a lot of configurations and tools included that we can use to drastically improve the way that stage 1 operates. Again, as I said, it is declarative, which means that we no longer have these large fragments of shell scripting that we have to just concatenate into another shell script. We just get to use declarative unit files that declare the dependencies, again with arbitrary ordering and complexity. It is parallel, which means that as the system is booting up, the things that need to start don't have to wait on each other for no reason. This can, in some cases, though in my experience not too much, improve the performance, or the runtime that it takes to get through stage 1. It can make it a little faster. And it importantly comes with a lot of tools that we can use out of the box. We have so much custom shell scripting in the scripted stage 1 that we can replace with tools that come straight out of the systemd project that we don't have to develop and maintain ourselves. So I'll talk about a few of them now, and one of them, the first I'll talk about is the ability to use rescue and debug shells. So when the system goes into like a rescue or emergency mode during stage 1, you get dropped into a shell, and you get really useful tools like system control and journal control, which let you take a look at what's going on. What unit caused the system to fail to boot? And also, you can look at like specific logs and really use the power of journal control to see what information you need out of the journal. This journal also survives to stage 2, which means that once you're in stage 2 and the system's booted up, you can take a look through what happened while it was booting up in a really fine-grained, detailed way. And then finally, if you are messing around in the shell and trying to fix what went wrong, like say something was wrong with the way the file system was mounted, you can mount it yourself and then just run systemctl default, which will cause it to retry the default transaction, and that'll cause it to just try to go to stage 2 again, and it'll go straight back into it. We also have systemd networkd. So in scripted stage 1, we have a scripted networking implementation, which is just the simplest possible network implementation, and it's extremely unreliable. With systemd, we are able to use the systemd networkd stack instead, which is very reliable. It also comes with a declarative method very similar to units that allows for these arbitrarily complex network configurations. And so far, this has seemed to be significantly more reliable and easier to work with, while also enabling significantly more sophisticated network configurations. And the thing that networking is useful for in stage 1 is that you might use it so that you can SSH into the stage 1 and unlock, say, your root disk remotely. So you don't have to be at the keyboard to enter the password to unlock your root drive if it's encrypted. Or you might have like a network file system, or you might do remote attestation to acquire keys, anything like that. Next, we have systemd ask password, which is a common protocol for allowing services to ask for a password that can be provided by some kind of response. The scripted init RD uses a number of unpleasant mechanisms where most of the time it's just asking for a password directly on the console, and then like if you SSH in or something, you can enter the password on some other means and then kill that process or something, or use this like weird bespoke command that someone developed in order to enter the password remotely. But with systemd ask password, the service asks for it using this systemd protocol, and then you can answer it in your SSH session, or you can let Plymouth, which is the graphical boot UI, implement its own systemd ask password response protocol, and then you just get graphical password responses for free. And all of this goes through the same interface, so no one has to do any kind of special work. Now, another thing that you can do with systemd that just comes out of the box is the TPM2 or FIDO2 or YubiKey integration. Systemd crypt setup, which is how you do LUKS encryption, supports these things out of the box. And all you have to do is use the systemd crypt enroll tool in order to set up the LUKS slot for it. The scripted stage 1 has some really complicated shellcode for dealing with YubiKeys, and it's very unpleasant to work with. So it's very nice to have these things as an alternative that just comes straight out of systemd. These also really complement UEFI Secure Boot quite nicely. NixOS has a project called LanzaBoot, which can do self-signed secure boot for NixOS, and combining that with things like the TPM can be very powerful. Now, I have an example here that I'm going to just explain how the setup works. Now, you don't need to understand this, so it's going to get complicated and you don't need to worry about it. The point is just to show the kinds of things that you can do with this. So, on one of my servers, I have a root file system that is encrypted with ZFS native encryption. There's an asterisk there because I don't necessarily recommend ZFS encryption, but I'm using it because I can knock on wood. And This ZFS dataset is unlocked with a key file that is stored on a LUX volume. That LUX volume is actually stored on a zvol on the same pool. So you've got a virtual block device which exists in your ZFS pool, which contains a LUX volume that gets decrypted, and then that is used to decrypt the ZFS dataset. The LUX volume is unlocked with a combination of a TPM2 and a passphrase, which systemd crypt setup supports out of the box. That passphrase is entered over SSH, so I can unlock it remotely. Over a tailscale VPN, the SSH host keys and the tailscale state are stored on another LUX volume, which is also on a zvol on the same pool, which is unlocked automatically by the TPM with no password required. And this is so that we can share the stage 2 tailscale state and SSH host keys fairly securely while still requiring a passphrase for the root data set. So ultimately what we're accomplishing here is that we've got the TPM securing both the SSH and tailscale credentials while still requiring me to enter a password to proceed the boot with the root file system, all protected by the TPM. And I've got a visualization here, if that helps at all. But yeah, you can see we've got the ZFS pool stores everything. You decrypt the SSH keys by the TPM, so that happens automatically. You enter a passphrase over SSH. That combines with the TPM to decrypt the root key to unlock the root data set. Again, I don't expect you to care about this. This is a really silly situation to find oneself in. But the point is that you can do these really complicated things, and systemd both has the tools to do these interesting things like TPMs, while also having the ability to specify these orderings and constraints against each other in a really elegant way. So now I want to talk a little bit about the roadmap that we have for this, for using systemd in stage 1, because it is an alternate implementation of stage 1. So first of all, in 22.05, it was added as with an experimental note in the documentation where all you have to do is enable this boot initrd systemd enable option, and that'll turn it on. So for a lot of systems, that's all you got to do, and that'll make it work. In 23.11, we've removed that experimental documentation and called it stable. We think that this is going to work for the vast majority of people. So in 24.05, we would like to make it the default. There's going to be some minor incompatibilities, and in those cases, we will try to detect it and automatically fall back to scripted initrd. But we would really like to try and move this to being the default in NixOS. In 24.11, like I said, the scripted networking in particular is pretty unreliable, so we're planning on removing that particularly early, if we can. And then finally, 25.05, maybe. We'll see how the feedback goes. We would like to remove the scripted stage 1 altogether. And we, being myself and a variety of other NixOS maintainers, most of whom are in the NixOS systemd matrix channel. So this is kind of the plan that we have for it. This is the timeline that we've been working on. So that you can tell this has been in the works since early 2022. Oh, hello. Okay, that was weird. Sorry. So to conclude, really this is all about the small things, right? Stage 1 is realistically only a few seconds during boot. It's not relevant to the vast majority of your system's functioning. And really just one little option is what caught my interest and got me to start working on this. But in the end, it resulted in a massive collaboration between myself and so many other NixOS maintainers who I respect the crap out of. This little thing really led to a huge aspect of my history in open source. So if you take anything away from this talk, it should be, if there's a little thing that you're interested in with NixOS, whether it's a package that you want to contribute or a suggestion to documentation or one option that you particularly dislike, then you should go ahead and contribute because it can have a really big effect. Thank you. My name is Elvis Jericho. I saw you first. The vast majority of options, oh, sorry, thank you. So the question is about to what degree do we have compatibility? Will your existing NixOS config work if you just flip that switch that says systemd enable? And the vast majority of options relating to the stage 1 will work out of the box. There's a couple that won't. We know those ones, and they will automatically fall back to the scripted initRD if you need it. But so the main ones that will do that are things like those commands fragments that I mentioned at the beginning, like post-device commands, pre-LVM commands, those things. We have no intention of supporting those in the systemd stage 1. It's not exactly that we couldn't. We could create like a little synchronization unit, something that's like, it just runs that script fragment and orders that script fragment as a unit after all of these and before all of these. But really, that acts as a choke point that eliminates a lot of the benefits that we're going after here, right? It puts a choke point in the graph, it makes it less parallel, and also it preserves this imperative sequential style that we're trying to get rid of in the first place. So we think that it's better to instead just, when we see you're using that, throw a warning, say, hey, maybe try and figure out how to make this a systemd unit, and then fall back to scripted at stage 1. So throw a warning, it'll fall back? Yes, it'll fall back, yeah. Yeah, so that'll happen at eval time. So the question is, do we have some way to make smaller unit files? And I'm not sure I quite understand the problem. I see. So the question is, yeah, if we wanted to take, what we're using to create units for stage 1 and use that in some kind of other context, I think. Is that about what you're asking? Yeah, that I don't think really exists at the moment. I've heard of people trying to make things like that. I don't think it would really be anything to do with stage 1 in particular, but like I've heard of people trying to make it so that like you can use the systemd APIs that NixOS has in order to manage systemd units on like Ubuntu or whatever. So that exists. It's definitely not like upstream in Nix packages though. Okay, so the question is about bcachefs support, in particular with multi-device, and did you say encrypted? Yeah, multi-device and encrypted bcachefs file systems. That is a tricky subject. The big problem there is that there isn't really a good implementation of systemd within systemd for this sort of thing. The problem is that, like, the best way to import or to mount your bcachefs file system is with uuid equals yada yada yada, right? And that works great if you specifically use the mount.bcachefs helper command. But if you're trying to do anything abstract, it immediately gets torn apart because the like util Linux or even systemd, all of these things will see that uuid equals blah 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 and tear it down into an actual path, dev disk by uuid, all this stuff. And bcachefs doesn't like that. So there's a bit of a mismatch between how bcachefs is trying to do this and how everything else in the Linux ecosystem is trying to do this. And it's really hard to figure out how to fix that. So the alternative is that you can instead specify things by devices separated by colons yourself, but even that gets a little tricky because now systemd sees, oh, this begins with /dev, and it tries to wait on that specific device, but that device is one with a colon in its name that is then followed by other stuff that it doesn't realize are just more devices. So systemd just doesn't have a good way to do this. The reason it works in scripted stage 1 right now at all is basically luck. And it's really it's a tough situation, and there's a lot of theorizing going into how to fix that, but there isn't an answer at the moment, no. It would be really good to have some way to detect that. We don't have that yet, but that's something I would like to look into. However, I will note Bcachefs is an experimental file system, so I'm not going to feel too bad if we don't have the best support for it. Go ahead.
Is it at all desirable to move away from the custom switch root steps that we currently have, where we also do the NixOS activation and use whatever steps?
So he's asking about the step that we do at the very end of the scripted stage 1, where we do a switch root. And so the way that we do this in scripted stage 1 is we literally just run switch root, which automatically changes the root file system of PID1 to the new one, the real operating system's root. And then the way it happens when you're using scripted stage 1 is it runs your NixOS activation immediately as PID1. We had to change that up a little bit with systemd because there's one thing that we really want to be able to do here. Systemd can serialize all of its state, all of its knowledge about units and stuff, and pass that along in a file descriptor to the stage 2 systemd. We really want to keep that, but it doesn't do that if PID1 in stage 2 isn't literally the systemd binary. So what we have to do is run activation in a CH root as a unit within stage 1, in the systemd stage 1. So that's how we're doing it right now. And the benefit is that we get much better insight through tools like systemd analyze as to what was going on during stage 1. But yeah, we did have to do that a little differently. Okay. Thank you very much.